Hello guys, this is the presentation for our research study on topic Windows and the Linux random number generator. Let's start to introduce ourselves. My name is Hugh and I have two teammates, Yu and Ke. This is a very simple question. There are two images. Can you guys determine which one is generated by the truly random generator and which one is generated by the pseudo-random generator? The answer is the second one is generated by the pseudo-random generator. We can see that each line in the second image looks similar and they all follow the same pattern. So there are two basic concepts to design a truly random generator, unpredictable and unperiodic. To think about these two questions, what is unpredictable? So things produced out of control, that is unpredictable. So what is unperiodic? If we mix things from different resources, that will be unperiodic. So we can see the noise will be a very good candidate to solve these two questions. And actually Linux kernel is used noise to build and design its truly random number generator. Okay, from the research we found, there are four functions the Linux kernel used to collect noise. It can collect noise from I/O, keyboard, mouse, and the hard disk. Let's start our interesting part. This is a structure diagram for Linux truly random number generator. It is very easy to understand. We can classify all components into three categories: noise collector, entropy pool, and interface. I marked them with different colors. First component is noise collector. It collects different types of noise and converts them into binary data. Then, Linux kernel maintains three entropy pools, one input pool and two output pools. Collected noise data will be transferred from collector into input pool through mixing function and estimation function. We will introduce these two functions later. Each pool has its own entropy counter to keep tracking available entropies in the pool. Then, entropy data will be distributed from input pool into output pools. Later, we have two diagrams to show how these two output pools work. And after that, you will understand why they are called blocking pool and non-blocking pool. Finally, each output pool is associated with its corresponding interface. Users like us cannot directly access any entropy pool. Instead, we have to use interfaces to get random number from entropy pools. Then, this is the input pool. The size of input pool is 500 bytes. It is like an intermediate between noise collector and output pools. Each receives noise data from collector through two functions, estimation function and mixing function. Next, you will introduce about these two functions.
I will introduce the two building functions in the input pool, the entropy estimation function and the mixing function. Before going to the details, I want to emphasize that the entropy estimation function is applied when you want to mix data from the noise sources into the input pool. And after estimate the entropy counter in the input pool will increment the corresponding value. Entropy was initially defined by Shannon. To calculate it using computer, a naive thought is to replace the probability with the frequency. However, this empirical entropy is not applicable in Linux RNG because Linux RNG will refresh its state frequently and thoroughly. Therefore, you need to recalculate the frequency over and over again. Now I want to give you an example of how this Linux entropy estimation function works. Saying that you want to calculate entropy at G5 when there are 4 what you will to do is you will first calculate the first, second, and third differences and find the minimum of the three, and then apply in the log2 function. Now let us go to the mixing function. I still want to clarify that the mixing function is applied in two processes, the data diffusion process and the data transferring process. Let's see the implementation of the mixing function in Linux RNG. The mixing function will be applied in two cases. The first is a mixing function without input. It is the state updating function, and then you can also model the function to be the linear shift register model over a Gauss field. So each time when you want to update the state, the element in the pool will be shift right, and the element in the index 0 will be implemented by the feedback polynomial. Another thing I want to point out is that the feedback polynomial is responsible for generating the period. Therefore, in order to achieve the maximal period so as to reduce the collection of states, an ideal case is to pick the feedback polynomial to be the primitive polynomial of the Gauss field. And the only difference between the two cases is that the case 2 will XORing the bit extension of the sample data. And this is the formal definition.
Let's get back to our structure. Next, I will talk about output pool. The first one is blocking pool. Its size is 128 bytes, and it is associated with random interface. It is used in blocking mode. The advantage for blocking pool, it is truly random, and it outputs high-quality random numbers. However, its drawback is blocking mode, which is unacceptable for most applications. Below is the diagram to show how it works. The scenario is a user uses random interface requiring n bits random number. After the blocking pool receives the request, its entropy counter will minus n and determine whether the result is bigger than 0. If it is, the blocking pool will directly output n bits data through extractor entropy function. If the result is smaller than 0, for example negative x, the blocking pool will require x bits from input pool. The entropy counter in input pool will minus x to determine whether it has enough data. If it is, input pool will transfer X bits into blocking pool. Otherwise, input pool will wait for collector collecting entropy until it has enough data to transfer X bits into blocking pool. That's why we call it blocking mode. So next is non-blocking pool. Its size is also 128 bytes, and it is associated with unrandom interface, and it is using non-blocking mode. The advantage is truly random numbers are generated when the entropy counter is not zero, and pseudo-random numbers are generated when the counter is zero. Most importantly, it does not block. For most applications, pseudo-random numbers are good enough. Its drawback is its output may be a pseudo-random number, which is less random quality. The scenario is similar with before. The user use non-random interface requiring n-bits random number. When the non-blocking pool has enough data, it works same as blocking pool. It could output truly random numbers. If the counter minus n is smaller than 0, non-blocking pool will use its pseudo-random function to generate n bits data. Then the n bits pseudo-random number will be output through extract entropy function. We call it non-blocking pool because users never need to wait when they use unrandom interface. As I mentioned before, both output pool have used extract entropy function. So next, you will introduce this function.
Okay, so now I will introduce the extraction function. I want to point out that the extraction function is not only used in the data transferring process, but also the output function. The extraction function contains two phases, the feedback phase and the extraction phase. So here, as you can see, there is a shaving function and a mixing function in the feedback phase. Therefore, the feedback phase is intended to update the state so as to prevent attacker from inferring the previous state. As for the extraction phase, you will apply in the 5-word hash obtained before as the training value for the hash1 function with the 16-word input. And the output of the shaving function is a 5-word hash. Now, so in order to obtain a 10-byte output, you still need to apply in the folding algorithm.
So next I'm going to talk about Windows Random Generator. So this shows the general structure of the Windows RNG. It uses RC4 cipher. RC4 is a string cipher. And as you can see here, RC4 has an S box, and it can generate infinite outputs. And this is a random string. Usually this random string is used to encrypt the plain text. And of course, here we don't have a plain text. Next, the result is add to the register R and state, and finally into our SHA-1 function, and the output is 20 bytes. So after 20 bytes and 20 bytes, of course, it reaches its limit. And the reason we have a limit here is because we can't use one short key forever. If we use one short key forever, the attacker will know the current state and guess the next state of the function. And so they can get the output. So after reaching the limit, we have to get a new key. And next, we're going to talk about how to generate a new key. So with Linux, Windows collects a lot of different noise from a lot of different functions. For example, get current process ID, get current thread ID, get local time, and etc. The collected system entropy is composed of up to 3,584 bytes of data from different operating system sources. These data are, together with 80-byte retrieval variable named seed, are hashed using the function called very large hash to produce the 80-byte digest. And these digest goes into 2 runs of RC4 encryption, and the RC4 encryption produces not only 80 bytes of output, and it is used as the seed for the next round, and the final output is 256 bytes, and it is used as the RC4 key. So, of course, the RC4 key is used in the RC4 function, and it gets a lot of random bytes, like we talked about it on the last page of this presentation. Finally, we're going to talk about the differences between Windows RNG and Linux RNG. And the first big difference is that entropy sources are totally different. In Windows, it has many sources, but it is not usually user-based, and it is the reason why it needs so many sources. And in Linux, it is physical-based, so it's actually mouse movement, keyboard input, and etc. Next is the performance. Windows RNG relies heavily on the performance of the algorithm, while Linux uses a mixing function. And mixing function is actually much more faster than the algorithm. Next is receiving and rekeying. In Linux RNG, it is feeding the state with system-based entropy in every iteration and whenever the system events happen. While the Windows RNG is receiving this state only after generating 128 kilobytes of output. And the collection of entropy in the Linux RNG is asynchronous. It means that whenever there is an entropy event, the data is accumulated in the state of the generator. In Windows RNG, the entropy is collected only for a short period of time before the state is reseeded. In the long period between reseedings, there is no entropy collection. Lastly, is the Linux RNG is implemented entirely in kernel mode, while a large part of the Windows RNG is running in user mode. This means that an application that runs in Windows uses the Windows RNG can read the entire state of the Windows RNG, while the Linux RNG is hidden from the Linux applications. And compared to Linux, it is easier for the attacker to obtain the state of the Windows RNG. And go back to the reason why we need to get a new key for the Windows RNG. Other than this, although the Linux and Windows RNG try to be more random, but there are still many drawbacks and flaws, you can see us discuss further about the existing and potential attacks and defenses to Windows and Linux RNG.